The remainder term of the Taylor series expansion is basically the remaining term that we truncated. But if we don't know the exact equation or polynomial, it is not easy to calculate this Rn. In that scenario, we need to have an approximation for this remainder term as well. And for that, we have an approach. And I will show in this slide how to use or how to have this approach to be able to predict the remainder term. So let's start for this approach with the n equals 0, 0 order Taylor expansion. For n equals 0, which is 0 order Taylor expansion. And we already used this before, and let's write it down here. The prediction of xi plus 1 is equivalent to only the first term, which is just the function value. And actually, if we say that this is the actual value without the tilde, which means it is the exact value, then we need to add the remainder term. And because this is the 0 order, the remainder term is R0. And this R0, if we truncate from here, let's focus on R0. R0 is actually, let me write 0 order Rn is R0, and we calculated with the remaining terms, which has actually the first term, including the derivative and step size, plus the second term, the second derivative, 2 factorial, and h square, and it goes this way up to the nth term or the infinity. So what we want to do is, like we did with the function value, as we said earlier, when we truncate from here, it just becomes, if we truncate, then we find the prediction, which is shown by tilde, xi plus 1, as the fxi. We will do the same for the remainder term. In here, for the remainder term, for example, we can just truncate from here and have an approximation of R0 just only using the first term. So simply we truncate from here, truncate, then similarly we will have a prediction for R0. R0 prediction is equivalent to just the derivative of the exact function times step size. But the problem here, as I mentioned earlier, is that if we don't know the exact function, how can we know about the derivative of that exact function? So that means, let me write it down here. If we don't know the function fx, then we don't know the derivative of fx. That means we don't know this. This is a question mark. And in this case, there is a theorem, an approach to be able to predict the derivative so that we can have a prediction of the remainder term. And this theorem is called derivative mean value theorem. And let me write it down. Derivative mean value theorem. This theorem says if fx and the derivative of it, f prime x, are continuous, then there is at least 1 point on fx which has a slope The slope is actually the derivative, and this is just a prediction with this psi value, parallel, which has a slope f prime parallel to the line joining fxi and fxi plus 1. So basically, if you remember, in the Tyler series, we will always have a previous value and a current value xi plus 1, and we will know the function values, and we will have a line between them. Then the slope of that line will provide us the derivative, basically. Let's show this in a graph. On the left hand side, I will plot a graph of a function, a hypothetical function over here. Let's make it better, like this. This is fx and this is x values, and let's say this is our function, like this. It's just smooth curve, and so assume that we have an xi value here. Let's say xi is here and its function value is over here, fxi, and we will also have an xi plus 1 value, and its function value is over here, fxi plus 1. So if you check this term from the end, so we will have a line joining fxi and fxi plus 1. So this value and this value, we will join them. Let me join them with a blue color, like this, a linear straight line. And it will have a slope which gives us an approximated derivative. And it says, so with this slope, there is at least 1 point on fx. In the fx function, there is only 1 point which has the same tangent or same slope of this. And actually, we can find it somewhere. So we will find the tangent point on the function. Let's show graphically with maybe green color, maybe over here. There is a tangent which is parallel to, which has a tangent. I couldn't draw parallel. It should be parallel to the blue line, actually. Let me draw again. Like this. So this one is parallel to this one, simply. And because this is a tangent, basically it is a derivative. So, and this point over here is the x value of this is shown by this symbol. Now you can call this psi, and of course its value, okay, it is similar to fxi plus 1, but it's not actually. Let me put it a little bit. So here the fx value is here, but that's not important really. We are only concerned with this, and actually we are not even concerned with that. We don't know that value. We are only concerned with the derivative of it, and this is also a little bit below. Let me write it down here, fxi plus 1. And what I mean is that, so we have a parallel line to this line which connects to the fx values of xi and xi plus 1. This parallel line, wherever it is tangent to the function, that point gives us a derivative which is similar to this one. So this derivative is our derivative here. an estimation. That's why if we find the slope of this, we can find the slope of this. That means we can find derivative. That's that simple. And over here, basically this distance here is h, step size between xi plus 1 and xi, and also there is this distance, and this distance is between fxi plus 1 and fxi, so the difference of these, and this basically gives us the R0 value. We can understand how it gives R0 value by this function. If we isolate R0, you can see that fxi plus 1 minus fxi gives R0. So here fxi plus 1 minus fxi, which is this distance between these, gives R0 value. So that's why by using the slope of this curve, this slope, which is actually this, the ratio of these tangent, let's have the tangent, these are the same, then the tangent is basically the slope is R0 divided by h, and if we can say that this is the derivative of this symbol. So that's why if we isolate R0 here, from here, if we isolate R0, that is the derivative times h. So this is very important, and this gives the slope of this as well. This slope is also the derivative of this. So this is the basic theorem, the derivative mean value theorem. And then we can say then this value marks the x value where the slope occurs. So we can extend this assumption to the higher orders, because now we found R0 as this, and we know this value through this slope. We can easily find this prediction. We know this and this one. We found the prediction for 0 order, but for higher orders as well we can extend this. Here, higher orders are just extension of this theorem, of this. So for example, R1 is simply the prediction, we can say, the second derivative psi divided by 2 factorial. So basically we truncate from the second, for the second one only. So we make this truncation here, but this time we have only the second term because it's R1. We only have this term. For R3 we will have the third term, for R4 we will have the fourth term, and it will go that way, so that we can find a prediction for the remainder term.